do is the anomaly conditions for the construction of the standard model. So I'm going to start with the charges. Okay, so I will assume that everybody knows that the standard model is SU3. 3 cross SU2 left, cross U1, which is a mixture of left and right. It's neither left nor right. Okay. The first fact is that the SUN charges are fixed. Okay. If you have F mu nu with d mu a nu minus d nu a mu minus I G F A B C A B A C, this G defines the theory, and then all the covariant derivatives on the fundamentals is d mu plus I G lambda A over 2 A mu psi. So those two G's have to be the same, and you can't have a quark with charge 2 if you want. But the U1 charges are not fixed. Okay, so just think of QED. We tend to think of the fundamental charge as E, and then the electron Q E minus is -1, the electric charge of the up quark is 2/3, etc. But we could use some E prime, which is, let's say, E over 3, in which case the charge on the electron would be -3, and the charge on the up quark would be 2, etc. So there's an intrinsic ambiguity in the definition of the charges for U1s. Okay, so we have, in this case, we have d mu is d mu plus I Q E A mu, where the product of these two is physical, but the absolute value is not. All right. So with that said, let's go straight to putting the charges in the standard model. Okay. So the first fact is that the left-handed chirality quarks are in doublets, SU2 doublets. So I'm going to focus on SU2. Okay, so the psi quark doublets, taking one generation, is up down. Psi lepton doublets is nu E. These are only the left-handed particles. Okay. So that clearly raises the question why, but we won't answer it. but certainly it's experiment. Okay. 2. We're going to take SU2 left cross U1 of hypercharge to U1 of E and M. Okay. So there are 2 conventions we need to do. We need to on both these U1s, we need to define a normalization convention. So there's 2 conventions. Okay. For the U1 hypercharge, we'll call the charge G1, and we can choose any value for that. I mean, if there's any normalization. We will just arbitrarily choose the charge on the electron is -1 in these units. Okay. For U1 E and M, the convention is the charge is E, and again QE is -1. Okay, so in general the charges, the electric charges, this is the E and M of some particle I, will be related to the isospin quantum number. It's called T3I, plus in general B times the hypercharge quantum number. Okay. These conventions tell us well, there's in fact a convention there also, so we could put A and B as arbitrary. These conventions tell us that A is 1 by this E and M convention, and B turns out to have to be equal to 1/2, and we can see that from so Q is T3I plus 1/2 YI. Okay. To check this for the electron, the -1 is the definition of the charge there. Its isospin quantum number is -1/2 plus 1/2 times -1 was its hypercharge by definition. Okay, so that works out. Okay. So there's really no physics in what I just did. This is just conventions. The next ingredient of physics is we have to impose these anomaly relations. Okay. So if we call the hypercharge gauge boson B, the fact that there's no ZBB anomaly tells us that we have some trace of T3Y over all the particles is 0. If there's no triple B coupling, it says that there's the trace of Y y is equal to 0. There's no coupling between this hypercharge and the gluon's trace of y lambda A, lambda B. Those are the matrices for that have to be 0. Okay. So there's a set of conditions. These actually are the most important ones, the most difficult to satisfy. This sets a constraints on the hypercharge assignments. So that's the physics input. And the last physics input that's needed is that E and M is vectorial. Okay. What this means is that there's, for every left-handed particle that you find, there's also another right-handed partner with QI left is QI right. So that's also an ingredient. Okay. This doesn't have to be the case. I don't know. This is of course an experiment, but you can construct theories where that's not the case. I mean, there's no reason it has to. It does mean that you can't give the particles a mass. Okay, if you gave these particles a mass, then you can go from one frame to another where left and right switch. But if they're massless, you can construct theories where this isn't true. Okay, but if you do these 4 ingredients, the 3 pieces of physics and the 1 set of conventions, all the charges are determined. Okay, so I haven't yet said 2/3, 1 minus 1/3, but that actually is forced on us now. All charges are forced. Basically by the anomaly conditions. Okay. So the fact that the charge of the up quark is 2/3 is now known, even though you'd have to do a little algebra to do it. So here's the assignments. Here's the particles. Here's the hypercharge assignment. Okay. The left-handed electron is hypercharge -1. That was our normalization. The right-handed electron is hypercharge -2. The left-handed neutrino, well, that's it's hypercharge is -1 also. That's actually fixed. That has to be the case because it sits in the same doublet as the left-handed electron, so it has to have the same hypercharge. So the whole multiple, it has to have the same hypercharge. But the right-handed electron, right-handed neutrino sits independently. Doesn't sit in a doublet. Its hypercharge is 0. The left-handed up quark is forced to have hypercharge 1/3. The left-handed down quark is also a third then, because it sits in the same multiplet. The right-handed up quark is hypercharge 4/3. The right-handed down quark is hypercharge minus 2/3. So these guys show that the U1 doesn't conserve parity. Parity is broken there. The right-handed and left-handed ones have different hypercharges. Just like I said, they could have different charges, but when you put this all together, all of the charges come out to be the usual charges that you know and love. So the covariant derivative here, psi, is d mu plus g1 y over 2 b mu, that's the u1. There's an ig2 tau over 2 dot w mu plus ig3 lambda a ga mu over 2 on psi. And of course these guys are for doublets, and this one is for quarks. Okay. So this structure is forced on us by those conditions. And the last thing that's interesting out of this is that the right-handed neutrino has no gauge interactions. Okay, it's not in a doublet, it's not a quark, its hypercharge is 0, so it doesn't interact with any of the three gauge bosons. All right. Yeah. Why don't I stop there? So that's the connections of the anomalies to the standard model, is it forces these assignments. Okay. We'll come back and we'll do more standard model stuff next time. Any questions about it? Yes.
Originally, neutrinos were thought to be massless.
Right.
So was there even a need for right-handed neutrinos?
There's no need for it if there's no prohibition either. Okay, so since the charge assignments come out that it has no gauge interactions, if you also, when we write out the Yukawa interactions, the Higgs boson interactions, if you also set one of their couplings there to 0, then it doesn't couple to the Higgs either, and therefore it you could throw it away. So it has no coupling to anything. So it could exist or it could not exist. You just don't care. But you know, it's always been true that there could have been a coupling there to the right-handed, to the Higgs. You see, it's perfectly allowed. It's not forbidden. It's not like this guy. There's nothing forcing it to vanish. You just set it to 0 just because we never saw a neutrino mass. Okay, so we'll do that story, and the seesaw mechanism and all that. Okay. Good. Let's stop there.